basically. Now, on a serious note, there's been a change in the rules. It used to be, and if you had an ARRL manual or an ARRL antenna book, you could see from that it was automatic exemptions were granted from having to do a station evaluation. Now they're no longer offering that automatic exemption. Instead, why don't you pass these around in pairs, let everybody just take a look at them. Those are on the groups.io files in the same place that the workbook is located. But basically, it used to be that you could simply say, okay, my 80-meter band, if my PEP power, and everybody knows what PEP stands for, right? Peak envelope power. If my peak envelope power on 80 meters was 500 watts or below, I don't have to do an evaluation. Well, they've changed that now. All right, okay. So now this new requirement is you do a simple check to determine evaluation is required. And there's a worksheet A and a worksheet B. And the worksheet A is to determine, do I need to do an evaluation? The worksheet B is basically an oversimplified evaluation, and it is grossly oversimplified. You actually probably can get away with a lot more power than you would get away with that if you looked at everything, which we'll do in the workbook. And using my workbook, frankly, it's easier to just go ahead and do an evaluation than it is to go through the process that the FAA or FCC wants you to go through. Also, for what it's worth, there seems to be no requirement to keep any documentation. We're trusted. In fact, the FCC made it clear in the stuff that I read that they're confident that licensed amateurs are competent to do this. And it is simple. The licensed amateurs are competent to do this and will. We follow the rules. So with that said, it's pretty easy to do. Now, if we look at new or modified stations, by modified stations, I've added a linear amplifier or I've changed the antenna, then this process is required to do now. If it's an existing station that I haven't changed since May the 3rd, I don't have to do it until May the 3rd of 2023. I don't get that because, again, we're going to make it so easy that you can do it anyway. All right. And I mentioned that there's no requirement to maintain records of compliance. With my workbook, if you've got a color printer, you can just print out the pages on the workbook and set them aside if you choose to document what you've done. This is a scan, basically, or a cutout of the worksheet A, the categorical exemption for station evaluation worksheet. So basically, what you're going to start out with is your peak envelope power out of your radio, and then calculate the loss in your transmission line. So they actually provide us with a table. I have this table in the workbook. This table is modifiable. So if you wanted to change and add your favorite coax or feed line to it, and you have the specific loss per 100 feet, loss in dB per 100 feet at any given frequency range, you can plug that in here and add it as a table. So basically what they're saying is, all right, I've got 60 feet of RG8 coax, and on 40 meters at RG8, let's say it's the RG8 foam dielectric, that's 0.4 dB per 100 feet. So 60 feet over 100 feet, or 0.6 times 0.4 equals 0.24 dB of loss in that 60 feet of coax. And then you're basically going to put that into the, you got feed line type, feed line length, and then the line loss per 100 feet. And then you're just going to follow their directions just like you were doing your income taxes 40 years ago. follow the instructions, and you'll come up with the 0.24 dB of loss. And then you're going to convert that into watts. How many watts of power am I actually losing in my coax? Now, once I've come up with how many watts how many watts of power I've lost, subtract that from the, let's say, 100 watts PEP that I have coming out of my radio. If that equals or is less than this amount here on the right-hand column for any given band, then I'm exempt. I don't have to fill out worksheet B. But if I'm above any of these numbers, I do still have to fill out worksheet B. Now, something that's worth pointing out here, I want you to notice that on 12 meters, 10 meters, and especially VHF, the maximum power output is significantly lower than it is even on the 70 centimeter band. The human body absorbs energy from different frequencies at different rates. And the magic frequency, believe it or not, it's not the microwave frequency, it's 2 meters, at least as far as damaging a living being.
That's how tall the body is, basically.
I suppose that could very well be. I hadn't even dawned on me. I know there is some in the documentation that FCC's put out, the papers that they had done, I don't know, 20 years ago, that talk about, well, you know, I don't remember specifically what it was, but it was basically what they had done to figure out how much a particular body is going to absorb. But it never dawned on me that, 2 meters might be it. Yes, sir.
Question from the audience. What impact does Bswr have on these calculations?
Excellent question. Tell them to sit tight, because we're going to answer that question specifically. All right. And you'll note that it is not in the FCC's mandated checks, but it can make a huge difference for you, because VSWR robs you of an awful lot of power. Okay, so we're going to take we're going to do an actual evaluation. So we're on worksheet B here, and we're going to take the results from the previous worksheet, and we're going to plug those in. And well, there's limited numbers of them, so pass them around, and you can see it up here if you look, since I've got worksheet B on the screen now. So A, B, C, D, E, and F, you're going to take off of worksheet A. And then you're going to deal with mode and duty factor. Okay, so when we're talking about mode, we're talking about the different forms of modulation. AM, single sideband, which is a form of AM, FM, slow scan TV, ATV, the digital modes. So there are a number of different modes on there, and they actually affect what happens to this. So just as a for instance, if I look at AM, we all know what peak envelope power is. What is average power? So if you look up here at the top, I got the RF frequency. I modulate it with this waveform immediately below it, and here's the waveform that I get now. So the peak envelope power is here from this point down to this point. But notice the peak envelope power is now much smaller here than it is over in this part. So if you took the integral, sorry to talk calculus here, but if you took the integral, which actually taking the integral will give you the area beneath this line, you'll see that you've actually calculated the average power. It's a fraction of what the peak envelope power is. And so everything that we're doing on the environmental safety, the RF exposure safety, is based on average power. So here's an AM average power. How about CW? Same thing. I've got a virtual square wave burst of energy at PEP but only for a short period of time. And then I have a period of time with no energy on it. So once again, the average is a small fraction of what the actual PEP is. Well, there's a table that the FCC approves, and I've got this table basically in the workbook, and it gives me what we're calling duty factor. So I've got CW, duty factor is 0.4. So I take my PEP power after the losses in the coax, multiply it times 0.4, and that's dramatically reduced my power again. Single sideband voice, notice it's 20% duty factor. But if I do a lot of heavy speech processing, it could be 50% of duty factor. FM voice or data, it's 100% duty factor. So depending on what you're doing, it's going to adjust your average power output.
This doesn't take into account the width of the signal, though, does it? Because, for example, it mentioned FSK on sideband as being 1.0, but that can actually have a lot narrower bandwidth. Say,
doesn't matter.
Okay.
It's the average power.
Okay.
All right. So your body's not going to discriminate from 147.28 and 147.0, right? So it doesn't matter. So it's just how much energy I'm actually putting out there total, okay, on average. All right, so the next step is I'm calling this duty cycle. Now, this is not what the FCC is calling it, but they're working on the minimum time the station's transmitting versus receiving. So if you look here, there's two periods of time that it works on, a 6-minute period of time or a 30-minute period of time. And that depends on whether or not you're in what's called a controlled environment or an uncontrolled environment. In your house, you could consider it a controlled environment. So a controlled environment is, I know how much radiation I'm being exposed to for how long, and I can control it. An uncontrolled environment is your neighbor's toddler just on the other side of the fence has no idea that you're transmitting 1,500 watts on a dipole that's hanging right above the kid.
You wouldn't want to do that anyway.
You're going to be surprised. I'm going to blow your mind when we get done here. Seriously.
You wouldn't want to do that, but I'm saying that what I'm saying is we want to be more cautious than that in construction.
Well, and yeah, and that's the point of this. But what I'm going to blow your mind because it's going to make you're going to ask yourself, why is the FCC bothering? Okay. Because if that dipole is 35 feet above the ground, and you've got and you're running 100% duty cycle and 50% duty factor, you can blow 1,500 watts out there and stand right underneath that dipole, and you're perfectly safe. So again, what's really fired all this off was the broadcasting stations that are transmitting 100,000 watts.
And people have asked the Weather Service about the radar before, and like we always explain that it's the same thing where the duty cycle is so small, it's listening far greater than the time it's actually transmitting.
Right now, the radar station we had at Wallace Air Station in the Philippines, every 12 seconds on every piece of electronics that you could listen to, it rip. So if you had a cassette tape recorder, you're recording something, every 12 seconds, rip. So then when you played it back, you got it twice. You got it, the one you recorded plus the one from this was a 200-mile search radar. I was watching for Soviet aircraft coming from South Vietnam. Anyway, okay, so back to the minimum time the station could be transmitting in a 6-minute period or a 30-minute period. The 6-minute period is for the controlled environment. In the controlled environment, you can have a lot higher intensity of radiation than you can in an uncontrolled environment. So it narrows that window over which you must average how much energy is being put out there. So again, this is just a little quickie. I'll leave that to you to read on your own. But your neighbors, anything on the other side of your property line is uncontrolled any way you cut it. And for those of us who live in suburbia or in the big city, you're in an uncontrolled environment. I mean, I've got an 80-meter dipole, probably 3 feet at the most from my neighbor's fence on one side, and probably 15 feet from my neighbor's driveway on the other side, another dipole. So bottom line is, I'm going to treat mine as uncontrolled any way I go. Okay, so if we look at the duty cycle, it's basically how much time is it keyed down or transmitted versus listening. And 50% isn't necessarily 50%. And this one is the one that doesn't make sense until you get the quickie explanation. All right, so I have to take into account the averaging time. For an uncontrolled environment, it's 30 minutes. For a controlled environment, it's an average over 6 minutes. So supposing I've got a situation where I'm operating any mode, but I'm keyed down for 2 minutes, listening for 2 minutes, keyed down for 2 minutes, listening for 2 minutes. If I'm in a controlled environment and I average that over a 6-minute period of time, what is the percentage of key down time? So I've got 2 minutes of transmit it, 2 minutes of receive, and 2 minutes of transmit for 6 minutes total. But if I add that up, I've got 4 times 4 minutes of transmit divided by 6 minutes of time, or 67%, not 50%.
Right. Well, unless you reverse that, receiving for the segments and transmitting on one.
You have to be worst case.
Okay.
Yeah, no, and one of the things that I've got in the workbook here is that you can go in and put in, you can select controlled or uncontrolled, and then you can put in how much is TX and how much is RX, okay? But the workbook does the calculation for you. So whether it's 6 minutes or 30 minutes, the workbook will come out with worst case average, which in this case would be 0.67, not 0.5. Okay, so now you need to go through and put in your total power out, your duty factor, and your uncontrolled operating time percentage or your controlled operating time percentage, and get an average power. Then that average power is converted mathematically. It's a fairly simple and straightforward equation, and I'll show you how to look at the equation that I'm using, and it comes right off of an FCC document. And basically, as long as your power density is within these limits, this top one is for occupational controlled exposure. This bottom one is for uncontrolled exposure. As long as you're at or below that value, you're compliant. Fairly simple, fairly straightforward. So far what we've done is losses in the coax, and then average power based on duty factor and duty cycle. And that's all that's required, but you're cheating yourself. You could operate more power and still be well within the limits. This is overly conservative.
No, you haven't talked about the gain of the antenna yet.
No, sir, we haven't yet, but we will get to it. They do suggest adding to the gain. You know, you have to consider the gain of the antenna in it. I'm not going into the details on how they calculate it, but the equation that's derived that I'm using is fairly simple and very straightforward. And again, I'll show it to you on the workbook. It's easy to get to. All right, SWR. Supposing I've got a mismatch between my feed line and my load, the load being the antenna. In this case, I was able to use a Smith chart and calculate that my impedance at the load is 32.5 R minus J300X. Has everybody got an antenna analyzer? Does everybody know where they can borrow one? Okay, how many of you been in on the classes on the Smith chart so far?
Well, was in on the class. I never retained very much.
Well, it's okay, because I'm going to show you, because the purpose of the class on the Smith charts and working the Smith charts is so you'll understand what's happening. We got computers now. Everybody's got a computer, right? How about if I show you some free software that'll do all the Smith chart calculations for you?
Call Nano VNA. Call Nano VNA.
No, Nano VNA is an antenna analyzer, and it can only tell you what it sees right at its point. No, well, that's where we're going to start, but then we use the Smith chart to figure out what's actually at the antenna. Okay. Because ideally, what you want to know is what is the impedance at the antenna, not at the feed point not at the transmitter.
Well, I thought that was the only place to measure it. No, that's what the AM broadcast engineer, they'll measure it at the antenna.
Well, yeah.
So climb up to the top of your tower and put your antenna analyzer at the top of the tower and key it up and measure it. Or better yet, why don't you just measure it right at your transmitter and use a Smith chart to translate that into what's actually at the antenna. Does that make sense? Okay.
I'm not, yeah, we don't have a big particle or anything. Okay.
Right. Yeah. My two dipoles are like 35 feet in the air.
Got it, yeah.
Hanging from a tree. And guys, I ain't climbing that tree. Okay. I'm too old and have other issues. Okay, so let me point out a couple things here. First of all, an antenna is almost never resonant at the point that it has the lowest SWR. Almost never. SWR is based on impedance. If the impedance is the same here and on this piece, it's virtually invisible. If there's a difference in impedance, there's a reflection. That's how radar works. So you get a radio signal goes through the air, and the free space impedance to radio waves is 377 ohms. But the impedance of that airplane is something different. So based on the impedance of that airplane, it creates reflection and reflects that signal back to the radar. It's impedance. So if you can make the impedance of that airplane 377 ohms, now you know how stealth technology works. That's exactly what they're doing. Okay, so resonance means that the load is all resistive. There's no reactive component in it. But it doesn't necessarily mean that the impedance is the same. So in this case, I have a 50 plus J0 impedance ideally coming at, and it's meeting a 32.5 minus J300 impedance. So I'm going to get a reflection. So I got forward power goes to the load. Some of that power comes back. Guess what? Reflected power do not radiate. I can subtract that from my peak envelope power. And we're going to do that in this workbook. In this particular case, I was able to calculate that we only have 73 watts actually hitting the antenna.
Radiating?
No, not necessarily radiating yet. Yes, sir.
My understanding is that some of that reflected power gets reflected back again, and then but then it gets
reflected back again.
Some of it, like for instance, the example I think is like window line. You can deal with high SWRs because a lot of that power will ultimately get transmitted. So
that's a little more complex to figure out. We don't take that into account here, but in a lot of those cases, if for instance, if you've got like a Wyndham antenna where you got window line going up to the come straight down from the dipole to the ground, and then you got a balun at that point meeting your coax, you want to calculate the SWR at the feed point to the window line, because the window line now is radiating. It's a part of the antenna.
When you say window line, you're talking about the lateral line too, right?
Basically.
Yeah, there's different word, different language.
There's different word for the same thing. Yeah.
Twin lead.
Yeah.
Okay. Just different forms of twin lead.
But calculations
here you have, you're subtracting the reflected power and you end up with 73 watts.
I end up with 73 watts.
Non-reflected.
Non-reflected. Thank you. That's a good way to put that, because it isn't necessarily radiated. All right. There's one more little thing in here. Notice that this 32.5 minus J300 says this load is capacitive. See, I got a capacitor sitting here. How many of you didn't know that reactive power does not radiate? It circulates. It circulates and eventually heats up something. Because what happens with reactive devices, particularly when you've got inductive devices and capacitive devices together, is that they charge and discharge each other. So if I've got an inductor in parallel with a capacitor and I charge one of those up, let's say I charge up the inductor, and all of a sudden the signal changes state, the magnetic lines of flux that are storing energy in that inductor now collapse and induce a current in the inductor, which then goes and charges the capacitor. And as soon as the capacitor is fully charged, guess what happens? The inductor is fully discharged, the capacitor now begins to discharge into the inductor. As long as the inductance and the capacitance are an equal amount, it's resonant, and it'll go on and do that forever, except for the fact that there's current passing back and forth between them, and there is resistance in there. And so that resistance then causes it to what we call ring down. And so after a short period of time, it rings down to nothing. The first wireless communication systems were a generator and an arc and a tank circuit at the base of the tower. Basically. So you had this arc, like an arc welder, go across, creating this huge current that hits this parallel tank circuit at the base of the tower, and it starts to ring. And that's how you got RF at a particular frequency. And the frequency was chosen by the inductor and capacitor combination. All right, so
you're saying that reflected power,
Or that power is just
the reactive power that way is consumed that way. Yes, sir, that is correct. But we don't call it real power because it doesn't do any work. The work that we do on an antenna is radiating, and only real power radiates. So let's talk about this a little bit, because there's three components to power in an RF environment or in any AC environment. There's real or applied power. There's the reactive power, and that's the one that rings down and goes to waste. And then there's what's called apparent power. Since all the calculations on a Smith chart are based on voltage standing wave ratio or current standing wave ratio, then what it's really talking about is apparent power. My favorite illustration uses my favorite beverage. Remember this. This is the test at the end of the chapter here.
Is there going to be a lab?
No, but as soon as these guys behind us get that tap over here, there'll be a lab. Okay. All right. So this is my favorite illustration for real, reactive, and apparent power. The foam at the top up here does not get you drunk. Some people don't think it tastes bitter too. It just, you know, what's the point of the foam? Man, it looks good. The part that gets you drunk is this liquid down here at the bottom. So this liquid down here at the bottom is, we'll call it KW, that's from my days in the power world. That's the real power. This is the reactive power up here at the top, and the apparent power is the total thing. All right. And impedance has exactly the same, they're analogous. So the resistive part, or the real part, is the beer. The imaginary part is the foam, and the impedance is the total of the two.
That's something to do with face anyway. So.
Yeah. Now, if I've got two glasses of beer here that are the same height, foam and beer, but one of them is half foam, they're still the same impedance. No reflection. Okay, you can actually measure the reactive component in your antenna system by using an antenna analyzer. So you use that just to measure the impedance of your antenna system at the transmitter. Then use a Smith chart to determine the impedance at the antenna feed point. This will give you the most accurate results, because you really don't want to use the impedance at your transmitter. You can, it's better than nothing, but it's not as accurate as if I can use the impedance actually at the antenna, because that's where the reflection actually occurs. Not only that, but reading it at my transmitter, my SWR is apparently reduced by the losses. What I'm able to measure of it is reduced by the losses that are inherent in the coax. All right, so there's two easy programs to use that'll do all the work for you. One of them is called TLW, or Transmission Line for Windows. If you've got an ARRL antenna book, it comes with a CD, and TLW is in the CD, and it's free. It comes with it. But there's no place that you can just download it. You have to buy the ARRL antenna book. This other one is tldetail.exe. It's a free download. Actually, I think it's a little better than Transmission Line for Windows. It's a little more comprehensive. And I'll show both of those to you. There's a publication called ARRL's RF Exposure and U. It's available for download. And I've got I'll show you where it is. In the workbook, I've got URLs for these. So you can just click on them and get it. So and I did mention earlier that the FCC has confidence in licensed amateurs' competence and willingness to do this. There are no hard and fast procedures defined, only examples, and you only need to follow sound engineering principles, which I trust that I did in this workbook. Our workbook actually does an evaluation mathematically from the position of being in a close urban environment. Now, there are different ways that you can do this. For instance, you can say, all right, I know I've got a certain amount of power applied to my antenna. How far must I be away from the antenna to be in compliance? That's one that they go into. This one basically says, my antenna is where my antenna is, and my neighbors are where my neighbors are. I can't control that. Therefore, I need to know how much power I can output from my transceiver or my transmitter and still be in compliance. Which now brings us to the workbook. First of all, let's look at these two programs. This one over here, Transmission Line Program for Windows. So basically, I can come up here and select my coax, and he's got some specific performance on the coax in it. Then I can put down the length of my coax, the frequency that I'm operating on. This shows the characteristic impedance of the coax, gives me the matched line loss in dB per 100 feet, or if I mark this as 96 feet, which is what I've got at my house, that was deliberate, not 100. I shortened it from 100 feet in order to avoid being an odd multiple of a quarter wave off of any of the bands that this multi-band antenna works on. And then down here, I can select load or input, and I can put in what my resistance is. Let's say I've got 32.5 minus J10 reactance, and the sign is irrelevant. Then down here, this will show me the SWR at the line input, the SWR at the load. Notice that the load SWR is a little higher than the SWR at the line. And it will also show me the actual impedance at the load, which is 46.94 plus J26.6. And we're going to want to use that. We're going to want to be able to plug that into the workbook.
So you did calculate the SWR at the load, measuring at the line input?
Yeah.
Okay.
So right here, see, can you see my pointer? Okay, so the SWR at the line input is 1.67. And I can calculate that. I can calculate this figure here based on my SWR and this resistance and reactance here. Or basically, I'm going to calculate the impedance at the load and use the impedance at the load versus the impedance the characteristic impedance to calculate what the actual SWR is. Yes, sir.
How does the antenna height factor in there? Because I know, like, as you raise the antenna, it increases the impedance rises as you raise the antenna. Does that factor into this calculation?
No, it doesn't.
Because I've measured the impedance at the transmitter, and by the way, in the Smith chart world, that's the generator. By that, then I take into account the characteristics, the physics, if you will, of the coax to get to the other end of the coax, and then I can calculate what that difference is at the antenna feed point itself, and I'm strictly calculating that. Now, if you raise the antenna, it's going to change that at the antenna feed point, but it's also going to change it at the generator. So all I have to do is measure it at one point and then calculate it back to the other side. This other one over here, transmission line details, gives me a little more information. Notice it also gives me a Smith chart here. And this red is at the input or at the generator. This blue is at the load or the antenna. Notice that the SWR, so I'm reading SWR this way. This line on the left is all resistive. I'm inductive above it. I'm capacitive below it. That means I'm reactive. Look what happens when I change the length of the feed line. Ideally, if I had 92 feet of feed line at this particular frequency on this particular feed line with that particular input, I would be all resistive with a 1.5 to 1 SWR. Boy, that all of a sudden that makes me think, at least for this band, I need to have 92 feet of feed line. The idea that the length of the feed line is irrelevant is a myth. It's only true if the load is purely resistive. You put any reactive components at the load, hello, an antenna's got reactive components. It's got capacitance, it's got inductance. Can't help it. And if you're not at exactly the resonant point, it is not gonna be purely resistive. There's gonna be reactions in there. And the length of the coax makes a difference. So this is one of the coolest things that I can think of on this particular program is my ability to tune the length of that coax to get it resistive at the antenna input. If it's reactive, I have reactive power. Power factor is determined by the load, not the generator. It's determined by the load. Now, at the radio, I've still got some reactance. So I'm going to have some power lost due to reactance at the radio. But everything that gets to the antenna at this point is going to be resistive or real power. That doesn't mean it's necessarily going to radiate. I've still got antenna efficiency to take into account, and I haven't been able to do that yet.
And this will be different for every band.
This will be different for every frequency.
So
yeah.
You're not going to be altering the coax length very much.
It depends on what kind of antenna it is. I've got a multi-band antenna, so I've got to catch a compromise to give me the best compromise amongst the different bands that I want to operate.
You can always have a coax tuner.
That's what I always called it.
You
Coax tuner.
You can do that. Now, if you've got a tuner at the antenna feed point, all of this is irrelevant.
Like for the SGC or something like that.
Yeah.
I'm sorry?
Thanks. Yeah, I was going to almost embarrassed to answer that question. Now I'm glad you said it. If I had an antenna tuner at the top of the antenna, a really good one. Yeah.
Yeah, and I'll show you how you compensate for that in the workbook. So let's go take a quickie look at the workbook. And we'll start off with the first tab. There's 4 tabs down here at the bottom. There's the cover, HF, the VHF, UHF, and SHF tab, and then the tables. All right, just a couple things. Notice here that everything that's in a light blue background is a user data entry, and everything in a yellow background is a calculated result. Now, I have protected this worksheet so that you cannot accidentally break it. But I'm making it possible for you to deliberately break it if you should choose to. And that is, you just go in and enter the password. So you go over here to File, Info, Protect Workbook. You just pick whichever one of these worksheets and say Unprotect, and then you enter the password. But what's the password? Well, gee, isn't it funny that I put it right up here, AF5YT. The only difference is that it's lowercase.
Why would you want to do that? Why would I want to break it?
You may want to modify it.
Okay.
Hey, you're a smart guy.
No, I'm not that smart.
Okay. So I'm gonna start out here. I'm gonna pick. Well, we'll come back to this. This is the cover page. The tables are all over here on the Tables tab. So this one over here that I'm looking at is my different antennas. This one is unprotected. You can change this as you like. The yellow you cannot change. It calculates that. That's actually a gain factor. Notice that I've got a 3-element 10-meter Yagi. It's called a 10-3 antenna by the manufacturer. It's 8D. They claim it's 8 dBd gain. That's 8 dB above the gain of a standard dipole. And that's a gain factor of 6.3. So that means if I put 100 watts into that thing, that it gives me the equivalent signal strength along its strongest point of 630 watts. Or it's the, I'm sorry?
Through a dipole.
No. Yeah, it would be the equivalent
of a dipole having 630 watts. Yes, right. That's
correct. I think that 8 dBd gain is probably a little high. But the documentation, the manufacturer says 8 dBd, so that's what I use. I'll bet it's probably 8 dBi, which is isotropic, which is 2.15 dB less than a.
Want to sell antennas.
Hello, yeah. All right.
But you're about to say which was 2 point what?
2.15 dBi is 2.15 dB less than dBd. So 0 dBi, 2.15 dBi equals 0 dBd. Everybody follow that? We're doing everything on this system as dBd. So we're doing what's known as equivalent radiated power, not EIRP, but we're doing ERP. This next one down here is that table that the FCC published. You can modify this as you like. You can come in here and say, okay, I've got RG8 foam. Let's change that to my favorite LMR 400 Ultraflex. If you can get the manufacturer to tell you what the loss is per 100 feet for each of these different bands. Fill that in yourself and you can select it. All right, so now let's go back to the cover page. So on the cover page, I'm going to select controlled or uncontrolled environment. Notice when I click on that, I get a pull down. So switch to uncontrolled. Now I've got 100 watts coming into my transceiver or coming out of my transceiver. Now I'm going to tell you here that I've done something a little different to make this easier. Virtually all of the modern radios have got a power output selection where you can say 100 watts, 25 watts, 35 watts, 26 watts, whatever. Maybe you've got a linear amplifier. The linear amplifiers sometimes rate their gain in dB. Sometimes they rate their gain and say, all right, 100 watts input, it'll put 600 watts out. That's what my Heathkit linears will do. So I come down here and I've got this linear calculator. I put in 100 watts in. I want 1500 watts out. It means I've got 11.76 dB of gain. So I plug that linear amp gain in right there. And then notice right underneath it, it gives me my watts PEP or 1500 watts PEP output from the linear amplifier. That could be any number of different things. It might be 600, well, my Heathkit linears are 600 watt PEP linear amplifiers. So I put in the gain of my linear amp. If I've got a 200 watt transceiver and I don't want a linear amp, I can put in whatever value I want under the HF transceiver and put 0 dB in the linear amp. 0 dB means a factor of 1. 3 dB means a factor of 2. 6 dB means a factor of 4. 10 dB means a factor of 10. All right, now I'm going to come in here and work on the duty cycle. How many minutes transmitting versus received? And I'm going to choose an operating mode. Here I've got CW chosen. Maybe I'll come in here and put in SSB voice, no speech processing. So now I have a duty factor of 20%, a duty cycle of 53.3% in an uncontrolled environment. Uncontrolled environment averages it over 30 minutes. So I take the worst 30-minute segment. Not the next 30-minute segment's going to be a little better, but I take the worst 30-minute segment. Okay, then I choose my antenna. Here I've got a half-wave dipole chosen, and it's got 0 dBd gain. And then we have to talk about antenna efficiency. There is no such thing as a 100% efficient antenna. Efficiency on an antenna is a ratio of radiation resistance to the combination of radiation resistance and all loss resistances. This one is very, very hard to calculate. It's real easy for you to just put in 100% here and say, okay, just, we don't know what it is, we'll call it 100%. There is no 100%. There is no 100% efficient antenna. There are some ways to calculate the efficiency on a ground plane vertical that the ARRL antenna book talks about how to estimate it. I don't go into that here. If your antenna manufacturer can tell you this thing is 94% efficient, put it in there. If you're talking about an antenna that's less than a quarter wavelength in length and they're saying it's over 90% efficient, that's bullshit and onion gravy. Sorry. Antenna efficiency is directly proportional to the length of the radiating element up to a quarter wavelength or multiple, exact multiple of a quarter wavelength. Yes, sir.
Anthony had a question from the audience. What impact do you have if you're using an external tuner? And imagine, so an internal tuner has no effect, but does either one have an effect on the calculations?
If the antenna tuner is at the antenna feed point, then yes, and what you're going to have then at the antenna feed point is an impedance of 50 plus J0. And I'll show you where to enter that here in just a minute. Okay, feed line data. I've got two choices for where I can get the feed line data. I can either get it from that table I showed you. So there's a pull down, I choose that table, or I can use the Smith chart to calculate that. And you noticed on the Smith chart, the software I showed you, it gave you what the actual total line losses were, including SWR based losses. It gives that to you in one little spot. It's easy, it does all the calculation for you, you just enter it. So you select the Smith chart to make that entry. The length is in my case here, it's 96 feet. And if I've selected Smith chart, watch what happens. Watch this over here. Watch what happens when I change this to table. It gives me, it pops down here and says, okay, pick your feed line from the table. So I can now go to that table and let's just say I picked RG8 foam. Uh-oh. I guess I didn't, I boo-booed. So you're going to have to unlock the dadgum thing and come back and change the format. I'll do that tonight and change it. Well, I'll do that tonight and reload the thing. If I go to the Smith chart, then I can go in here and type it, and I'm just going to type in, my coax on this one is LMR 400 Ultraflex. Then I come down here and you see you've got these check boxes. I can check off and say I want to test these particular these particular bands. In my case, this particular antenna has 80 meters, 40 meters, 20, 17, 15, and 10 meters that it's capable of doing. So I check those. Notice what color this is. Those are green.
Green is go.
Green is go. Green is compliant. Now, wonder what would happen. Oh, by the way, notice that I'm 25 feet above the ground and 0 feet from the property line, and I'm putting out 1500 watts PEP. And notice that I can stand right up underneath that deadgum antenna and I'm perfectly safe. How about that?
How low could you drop that down to 10 feet?
Let's see, we'll just stick a 10 in here. Now it's no, but now watch this. Now here's the reason why I said put your gain of your linear amplifier in here. Your linear amplifier does not have a nice little adjustable tool that says, okay, here's how much power out I'm putting. I've got gain. I'm going to put, in this case, I'm going to increase the input power by 11.76 dB. So looky here, this thing says for 20 meters, this little number 41 on the right. If I go up here and put this 41 in right here, that's the power output. Now I'm going to dial on my transceiver. Look what happens 20 meters. It now goes green.
One thing I learned about 1500 watts.
The end of the wires on 80 meters, it can get very hot.
It can certainly be high voltage, yeah.
Well, short story. One time, somehow the end of, I had a little piece of the end of the antenna, flopping there, so you could trim it, whatever. But it's kind of flopping in the breeze, and came around there and hit an insulator. And it was on fire.
Yeah, well, if you're getting heat, you're getting losses.
Well, what I'm saying, no, I'm saying it's shorted.
The wind came around and hit the thing and started a fire. And
it's funny, my signal went to pot and I went out and said, well, let me look at the antenna. It was kind of wind's blowing. Well, yeah.
At the feed point of an antenna, the current is the highest and the voltage is the lowest.
I'm just saying it can be a fire.
Yes, it can. And at the end point of the antenna, the current is the lowest and the voltage is the highest. So yeah, so I mean, you got really high voltage over there. Another reason to make sure that your inverted V antenna is far away from the neighbor's toddler.
And it's in the fence too.
And the fence. Yes, sir. Yes, sir.
I can't see anything up there, but when you dropped it that 5 feet, what did it do? 10 feet, I'm sorry. It went from 15 to, or whatever you said, to 10 foot.
It
didn't work, right?
It basically said that, well, you're that much closer to the antenna, and so the signal intensity is that much higher. Okay. So the watts per square meter, or the watts per square centimeter, is higher than it was before. And this thing does all its calculation in milliwatts per square meter.
If you went the other direction, another 5 or 10 foot up, it would probably still be in the green, right?
Well, some of it might be. So if we go up to 15 feet, and let's go back to 100 watts.
Which says if you lower your dipole,
you put it at 1500 watt linear on it, your dogs are not going to be much of a problem.
It won't be digging.
So based on the spreadsheet you filled there, if we put our dipoles high enough, we could run 1,000 watts.
No, 1500.
1500.
Yeah, if you put, let's see. Now, again, it's going to be, once we get it hung, we've got to measure the impedance at the transmitter point, and then go to transmission line details and figure out what it is at the antenna and plug that in here. Yes, sir.
Kind of following what he said, are you going to bring this out to field day so we can practice?
That's the idea.
Awesome.
That's the idea.
And we have an antenna analyzer in that cabinet behind Mike if we need to use it. But I've got a couple of antenna analyzers, and I'll be bringing one.
I have my Altoid cam on it.
There you go.
So
let's see. Let's see how high I need to get to make this one clear. 20 feet off the ground, I'm safe. with 1,500 watts PEP and a 98% efficient antenna, which again, I don't believe. Now, let's jump over here to the HF tab.
I couldn't see it, but does that spreadsheet also address like 6 meters?
Yeah, yes. See down here.
Okay.
So I've got two tabs with calculations on them. I've got the HF tab, and it only displays those bands that I have checked. If I look over at this one, there's nothing displayed. But if I come over here and hit, I've got a 2 meter and a 70 centimeter dual band antenna. So I can look over here. Now, all of this has to change. But you'll notice that my 2 meters is red at 1,500 watts PEP, but 70 centimeters is green.
And you said that the
2 meters is really kind of the critical one. So
it's the most dangerous one.
And 6 meters too, right? So
usually,
yeah, but the 2 meter is actually a little worse than the 6 meter, although they've grouped them together for the exemption point. But actually, no, the 2 meter is a little more dangerous to us than the 6 meter is.
Got it. So it says you'd be compliant if you're at 95 watts, so you're pretty close to it. If you just raise the antenna a little bit.
Again, wrong antenna. So I would, if I was going to do that. So let's get rid of these.
So 100 watts in your car at 2 meters
becomes interesting because it's low to the ground.
Well, there's another.
You're also protected from the metal shielding in your car.
See this
you
thing?
Are.
No,
yeah, you're in control.
See this thing right here? It says full reflection. If I check that says I'm right on the ground, and so I'm getting basically double the radiation, or I'm right next to a reflection and I'm getting double the radiation. I suggest you just keep that checked, because it basically is then now taking how much radiation in milliwatts per square centimeter and doubling it and making the comparison based on that doubled figure. All right, but if I wanted to come over here now and check out my 2 meter 70 centimeter, I've got to change my antenna. So I'll come to my antenna. I'm going to do my dual band antenna, but the gain is different for 2 meter than 70 centimeters. So we'll do 2 meters first and unclick the 70 centimeters. And now I'm going to have to reduce this to a 68. Whoops, 68. And I know that this one is 30 feet off of the ground on my house. It's a vertical. And so now with 1,000 watts out, I'm safe, uncontrolled environment with that antenna 30 feet off the ground.
You change it to 100 watts and 10 feet.
What's the question again?
Well, I'm at 0 feet distance to the property line now. So
what I'm doing is
saying what happens if this is a mobile station. You run 100
all right,
watts
let's
from
do
your
this.
car, you're
Let's
ground
do
level.
this. Let's put it at 3 feet.
I suspect you're going to be green anyway.
And how many watts?
100 watts. So you run 100
All right,
watts
so
on a
let's
mobile
put
unit.
0 dBd in the linear. And looks like we're going to need to go to 50 watts, which is typically what a 2 meter radio will put out in your car, and you're safe.
Well, you want to try 100.
Try 100.
No, it's 52. I already
Oh,
did.
already know that.
It already know it says 52 watts. So put
Okay.
100 in here.
Oh, gotcha. Oh, yeah.
Look down here. It's red. And what's the number next to it? 52.
I tried to tell sheriff's office, they wouldn't
Anyway, so we can go up here and put in 50 watts, which is what your radio is probably going to put out, and you're safe in your car. All right, so let's go back to,
You have 3 feet. I mean,
Really, I mean, my car is going to be more like 5 feet. But,
yeah, do
well, I guess it depends on where the antenna is.
You just get better from there.
Just
Yeah.
right.
Okay.
All right. So my antenna is 33 feet above the ground. distance to the property line is, I'm just going to say 3 feet on this one side. So it calculates the distance using Pythagorean's theorem, the distance to a 6 foot tall person immediately on the property line. And I'm going to put in 100 watts. And I'm going to go ahead and put in the 11.76 dB again. What did I do?
Putting it in operating mode. Go to the right side, Timothy. Push it a little closer.
All right, 11.76 dB. So doing single sideband voice with no speech processing, I'm calling CQ for 2 minutes, listening for 2 minutes, calling CQ for 2 minutes. And I've got I'm in a uncontrolled environment. So it's a 30-minute, it's a 30-minute average. So then I'm going to click the bands that this particular antenna system works at.
Your antenna is still set for 2 meters.
No, I'm sorry. Thank you. I need to put my dipole up here. Mine is a dipole. It's an off-center fed dipole. It doesn't matter. It's a dipole. It's a half-wave dipole.
35 feet is the feed point of the dipole. What if the
yes.
What did the height of the ends matter, or do they?
Go ahead and just use the feed point.
Got it.
Yeah. If you want to be anal about it, average it.
Okay.
All right. It's up to you.
You count an in-fed as dipole?
Yeah.
No, but you could use a dipole for it, probably would work fine. But the efficiency is going to be a little different for an in-fed than it is for a dipole. Dipole will be a little more efficient. But I don't know how to measure and calculate that. When I say measure, I don't know how to calculate it. So now let's click on the HF tab. I'm going to use the Smith chart calculations. So what I did was I actually measured at my transmitter the R and X off of my antenna analyzer. Then I used transmission line details to calculate R and X. And the frequency that I have in here is the frequency with the lowest SWR. Because the biggest effect that I'm going to have is my SWR, how much is reflected. So I pick the lowest SWR and then get the feed point impedance from that. Now, if I take the square of R plus the square of X and then take the square root of that sum, I get a power factor of 0.93. So that now takes the amount of power I've got to my feed point times 0.93 is the real power. Everything else is reactive power, which does not radiate. I enter my SWR at this point right here, and everything else is calculated for you. You don't have to do anything else. You enter here, enter matched line loss in dB right here. So 0.214 was what transmission line details told me was the total, what was the matched line loss in the line. I actually then calculated the total losses myself because it was easier. That way I could come over here and say, all right, I'm going to use the table, select my feed line from the table, and notice that enter the match line loss has disappeared. But this has to be different for each one of these bands. Notice how the R and the X are different for each band. And guys, it's no more complicated than this. This is it. You now know everything you need to know to do an actual evaluation on your antenna. But you got to have my workbook, you got to have transmission line details, and you got to have an antenna analyzer.
What's the annual fee of your rate?
About $200,000. But we have creative financing. It's $0 down and $0 a week for the rest of your life. How's that?
So in a situation where you're out of compliance, say for instance, well, you had to reduce your power, change your antenna, move your antenna, or possibly change the uncontrolled environment to a controlled environment, if you can do that.
You can't do that at your house, can you?
What's that?
You can't do that at your house, can you?
Well, move to the farm and you can, but
Right.
Yeah.
But
Yeah.
you know, we generally live in the big city here, and so that's why I took the particular tack that I did and gave you the number that you plug into your transceiver that will get you in compliance, and that by the FCC is acceptable.
Now, if you can move your antenna further away from your neighbors, well, from your property line, that helps too.
Yeah. But that's a variable that you can change in here. Yeah, I mean, my 10-meter 3-element Yagi beam is in a different place than either of my dipoles. Yes, sir.
Can you factor in the orientation of your antenna?
No.
Okay.
No, it doesn't. But it really doesn't need to. Now, let's assume that you're on the edge of suburbia and your neighbor lives over here and over here, but it's 2 miles of woods back this direction. Point your antenna that direction, you know you're safe. But if it's a beam and you can rotate the beam and you can rotate it and point it over here, do you really want to roast your neighbor's toddler? They're teenagers, another story, right?
Like for example, satellite antenna would be a good example, because some of those will have like 22 the crosshatch 22 elements will have something like 14 dB gain to it. You can literally,
the satellite antenna could easily have
20 and 30 and 40 dB a gain. Yes.
And you can literally point that at somebody.
Yes, and hurt them. Yes. And that will, by the way, that this program will work that way. All you have to do is put the antenna in and the amount of gain. But what we're doing is we're assuming worst case that the strongest point of the load is pointed at your neighbor.
So we're really going to have to worry about that satellite system we're setting up.
It's going to be high enough. I don't think I'll be a problem.
It's going to be pointing up.
Usually,
and the power output is pretty low. Okay. So when you're talking about particularly those high gain, well, a dish antenna, you know, some of these microwaves, the output power from the transmitter may be as low as 10 milliwatts. But you got a 36 dB gain antenna.
And not many side lobes either.
And it's concentrated.
that's
where it's at.
Satellites, they encourage you to run as little power as possible, especially on the sideband birds, because you'll overpower the passband and basically use up all the satellite's power on your, because on satellite bird you can have 3 and 4 conversations going on satellite, and one person hits it really strong, the transponder will equally replicate that out as super strong. So I encourage people to use the minimum power it does to get the transponder, or else you'll have one person that just monopolizes and it causes everyone else to signal to get degraded.
the rule is,
whether you're talking to a satellite or anything else, is that as an amateur, licensed amateur, you use the minimum amount of power necessary to do the job.
That's actually a technician question.
And it's a regulation. It's a rule. It ain't a suggestion.
And what you said here, you're gonna have to be a big gun just to worry about.
That's my point. Why in the world is this such a big deal? You have even sitting in, just get the antenna up minimum height. And guys, I hate to tell you this, but Anthony, stop it. Anthony's antenna is not supposed to work. Minimum height for a dipole for 40 meters is 35 feet above the ground. At 33. But Anthony's does, I don't understand. This is 8 feet.
Well,
he's talking all over the world.
Straight up.
No, it doesn't. I hate to tell you this. If it was going straight up, he wouldn't be making contacts in Italy and Australia and.
Is it a loop?
It's a dipole. It's an off-center fed dipole stapled to the top of an 8-foot fence.
So I can't explain
Thank you. Stop it, Anthony. It's not supposed to work, and it's incredible how well it works. It just blows my mind. He's making contacts all over the world. Yes, sir.
Speaking of Anthony, he asked, do we need to evaluate our repeater stations?
No. Well, we're going to have to evaluate our Benbrook repeater station because it's all new as soon as we get it in. But the one on the tower is safe until May the 3rd of 2023. However, pretty easy for us to do. But we're really only running, I think, 50 watts.
Correct. I'm not even sure that maybe 25.
Say 50 watts on your
I think it's 50, but I'm not going to swear to it.
It's probably a little more than it is BB product.
It's a little bit more, but not much. Yeah, no, we're safe.
As far as out of the radio, I doubt that it's 50. It might be 40, but Tommy likes to keep all that tuned way down low.
Well, and that also depends on whether or not it's on the battery. So it'll be a little less on the battery than it is on AC power.
The old one before we shifted over to Yaesu, 17 watts, 17 to 20 watts on that old the old used stuff. Very, very low power.
That was a GE Master 2, wasn't it?
Right. The whole idea is height.
The other thing is how much usage is it getting? So how much time is it transmitting versus not transmitting? Well, the problem is that anytime it's in use, that duty cycle could be fairly high. Randy Thompson and I worked an exercise to see how long we could operate it, the .28 on a battery. And we made some assumptions. First of all, we got a 120 amp hour battery, figuring that we can use half of that battery because it's a deep discharge telecom battery. How many days could we operate on that battery without any power? And we said we could operate for quite a while on it. But one of the things that plays into that is the fact that the battery output is going to be between 11.8 and 12.6 volts. Versus 13.8, and that's dragging it down.
It drops to nothing after 11 volts.
It could very well be, but hopefully we don't drop it that low and ruin the battery.
Well, one of them we did, the one that was out at the 440.
Yeah, and it seems to be okay. We've got it back in here. Charge. You're talking about the Benbrook battery.
Correct.
Yeah, it's back in here. But yeah, it was completely dead. Completely dead.
And Mike quit pointing that thing at me.
All right. Any other questions? Yes.
Another question for the audience. HTs.
HTs are exempt. Their power output is low enough that FCC considers them safe. Strongly recommend that you guys download this thing. I will fix that little error that we found and come up here, go ahead and download RF Exposure and You. It's like a 58 megabyte PDF. It's very interesting. It was written by ARRL. It contains it's got some addendums in it that are excerpts from the FCC's regulations that apply to us. And it's worth a read if you're at all interested in the technology. It's really worth a read, and you'll see that they oversimplify it. I still oversimplify it, but I don't oversimplify it nearly as much as they do. So that you get a little more slack using my tool than you would get using this worksheet. It's on groups.io. Well, are you signed up on groups.io? Because I sent an email. Okay, so you go to groups.io. So it's cowtownarc.groups.io, and then you go to the main group, and then you go to files and RF exposure, and then you'll find the workbook and these worksheets on that folder, and you can download them. Something I forgot to mention to you guys, you see these these little red triangles up here, each one of those is a note. If you hover over it, a note pops up. And you want to know the equation. Now, this is a really complex equation. There's the equation that I'm using to calculate milliwatts per square centimeter based on PEP power applied to the antenna after all the losses and other things are taken into consideration. So if you want to know what's going on, how am I doing that? Just
That's how you get your pass-fail test?
that is exactly how I get my pass-fail test. If the power density output here is less than or equal to the power density limit, it's green. It's that simple. And now this power density limit is calculated based on the tables that I've got right over here, which I showed you on the presentation. So here's controlled environment tables. Here's uncontrolled environment tables. The electric field strength and magnetic field strength I ignore. You can use either one of those if you want, or do the easy thing and use power density in milliwatts per square centimeter. And that's what I'm doing. It's the easy one. And the equation for that, the derived equation for that is 0.41 times ERP divided by pi r squared. Oh, I forgot to mention that to you. If your check boxes don't work, you can come in here and click in the box next to it and put a 1 in place of the check or a 0 to uncheck it. It'll do the same thing. So watch what happens here when I put a 1 in that. Shows up as a checkbox, and then I go over here to HF and 160 will show up. How about that?
And the other option is if I'm non-compliant, I can always just unprotect your workbook and fill in the values manually to make it look like you're compliant, print it, and if I'm ever questioned,
sure,
there you go.
Sure.
Actually, yeah, it says we have to do an analysis. It doesn't say we have to.
Your math has to be correct.
Yeah. Okay.
Well, that's what I'm saying.
The math is so complicated.
Yeah.
That a 6th grader can do it.
Once we do a compliance, if we find we're non-compliant, are there any
if you look, if you look in this RF exposure and you, which is an ARRL publication, it talks about it. It's got a chapter on there when you've got trouble. What can you do when you're non-compliant? And one of the solutions is reduce power output. So you come up here, this thing tells you how much power output you can have from the transceiver. Plug that in, get your green light, print it, and you've got on here that I did the evaluation and it came out green. Make sure you got a color printer. Came out green with my transceiver RF power output X.
I guess the next question is, what are the penalties for being non-compliant?
There seems to be no.
Considering we're self-policed,
bingo.
And we have people that are transmitting illegally that are bigger threats.
So what's the scenario I would think is if you get a neighbor that complains, legitimately or not, and the FCC chooses to investigate it.
Well, it would go to an official observer, which is through the ARRL first.
Well, but what they're going to do is they're going to do an evaluation. And they're going to say, you're compliant. Or they're going to say, you're not compliant. You're going to say, yes, I am. Look here. You're not taking into account the fact that I've got an SWR at this point and reflected power, reducing my power output from the antenna.
The point is, you need to do what you need to do this process so that you can defend if that
Exactly. And
I guess
so
my
suggestion
is of the FCC coming knocking on you, even if they get a complaint, are going to be very low.
Yeah, I'd say is how if you know your neighbors and you got cool neighbors.
And
probably
the magic word is, as you said, we are self-policing.
Correct.
And that's what the FCC is counting on. We're like, we're not amateurs because we don't know anything. We're amateurs because we don't get paid.
I can tell you, I've had someone dead to rights, keying a radio, interfering with the Racing's net, knew exactly who he was, had it on tape, and the FCC still wouldn't do anything about it. Finally, we got some other people local involved. At least we got stopped, but there was no fine involved.
Okay, so this before I left, I'll show you how to do this since you guys, let's see, file info. Then let's see, it was the cover that I needed to unprotect. So then lowercase AF5YT. Now that's, then I go back over here, select feed line, format cells, protection, unlock and uncheck the locked. Okay. Now I'm going to switch this back over to Smith chart and make sure that I did this one also. Format cells, protection. I didn't unlock it either. So now it's unlocked. So anytime you bump into a problem, you've got it. I'm going to save my work. Then I'm going to go back over here and relock that sheet. Info, protect workbook, protect current sheet. I'm going to enter AF5YT. Repeat. And now it's protected. And so now I can type something in there.
I'm in her district in South Fort
Or is the password listed on any of the sheets?
Yes, I'll show you here in just a second. I'll show you again.
Well, I know it's on the cover.
It's right there. No, that's it. It's the same one, but it's lowercase, not uppercase.
I'm wondering why you don't just go ahead and put the password for this is AF5YT in lowercase.
Because I'm telling you, I don't want to open it up to the whole world. And you know, anybody that's an amateur is probably smart enough to know, well, I know what that password is going to be. It's his call sign. Bingo. You know, I've got one that does it's a design simulator for solar powered chilled water systems, and it's NCC 1701. It's the
Enterprise.
Anyway. Okay, so save it. Yeah. Hey, how many guys did we have come in on the Zoom?
We had 11, well, 9.
So we had a pretty good
But you're
turnout.
popular. You did
I
great,
must
by the
be.
way, but excellent presentation.
Don't give me a big head.